This title of this presentation could also be rewritten somehow as model-based mechatronics using Modelica, because in fact this is what we do. We just use a Modelica-based framework to run in real time some models of dynamic systems and use them to both design control systems and to verify what was already designed before. Um, and the scope of this presentation starts with an overview about our activities here at MWF, our Modelica libraries, which were developed in-house in and used in many different applications. And then I go through the specific applications in which we used all these Modelica libraries. After that, I provide a quick outlook about what is the current status of these libraries, what are we currently doing with them, and what are our plans as next steps for these libraries. So we started in 2012 working basically with product development, but very strongly with model-based product development. Not only electronic systems, but also mechanical, and currently we can say that we are specialized in mechatronic systems, both complex systems and other systems which are simpler and composed by um, many different devices and mechatronic subsystems. So our workflow is very simple. Once we have a specific Modelica development environment like Wolfram System Modeler, we generate a compiled version of the model called FMU under the FMI standard, and we run this model in real time under Linux with a PreemptRT package. After that, we are able to interact with the system in real time through real-world signals. I mean analog signals and digital signals. And we are able to do all this in real time with a rather complex dynamical dynamical system representation. This is one of our platforms. We call it Qfire Hill. As you can see, it has inputs and outputs for real-world signals, both analog, digital, and also digital buses like CAN bus, which is very common in agricultural machinery and commercial vehicles, for example, or even maritime applications and many others. The interesting thing here is that we are able to run uh, sim, some we can run complex models with dynamics and event-driven behavior, even mixed with dynamics or just event-triggered behavior. We can run these models and see how the signals evolve in time and check how they interact with a real external controller by means of this platform. So throughout this presentation, you are going to see that we apply more or less the same workflows. We just change the specifics of the models and the applications, but everything is based on this very simple workflow. This could be done manually. I mean, we could generate the FMU and then adapt this FMU to run on Linux with real-time capabilities and um, communication with a data acquisition board, for example. But we have an automated workflow that allows one to generate an FMU and directly load it into this framework to run it in real time and interact with real world signals. So these are our main libraries. These names are the names that we use internally. We do not make them commercial, so we don't sell these libraries. We just use them in our own projects. We call them Aquanaut, Heavy Dynamics, and PMSMC. The Aquanaut library has models for vessels in the presence of waves, ocean currents, wind, and many other interactions with different actuators like thrusters, rudder, bow thrusters, and so on. The Heavy Dynamics library is mainly devoted to commercial vehicles, but especially commercial vehicles driving on hard soil. Another version of this library was developed also for soft soil and interaction with rocks and so on. I'm going to mention this very briefly, but this current version is dedicated to the simulation of heavy vehicles on hard soil. PMSMC means Permanent Magnet Synchronous Motors Control. This is a library that models accurately uh, PMSM motors and generators and are able to help the designer to design specific control systems, design inverters, check the short period dynamics, and design other types of converters as well, like many different types of rectifiers, inverters, speed drivers, and so on. So they were all developed in-house completely, and they are used in our own projects. And now let me dive into our specific applications using each one of these libraries. First, a brief introduction about the Heavy Dynamics library. Currently, we use it to model and analyze and even design control systems for heavy vehicles. But originally, it was conceived to simulate planetary exploration rovers like this one that you see in the animation there. This is, in fact, an animation at that time. It was developed in the first version was developed in Daimola, but it runs in System Modeler, Open Modelica, and many other Modelica-based um, packages. And as you can see, it is able to reproduce the trafficability of a planetary exploration rover with many wheels in contact with soft soil, in contact with stones, many stones at the same time, producing tracks on sand, different types of sand, etc., etc. Both sinkage, slippage, both lateral and longitudinal are able to be modeled and simulation in this library. This first version was very important to give us the basis for the development of the contact models, which are the most important features that we have in the current version of this library. Although it was originally conceived for both soft soil and hard soil, uh, soft soil applications are not that frequent for us, and for this reason, we further developed the library to work with hard soil only. And this is one of the most interesting applications that we have. This is an electric tractor, a four-wheeled vehicle. Although in many situations, it would be interesting to simulate it in soft soil, but it is entirely simulated in in hard soil, and this is very useful for us to help us to understand the dynamics of the vehicle, the power demand, how the power is demanded for every component and for every device in the power electronics uh, pipeline, and how the motors are going to be demanded during the specific use case. So this is one of the applications. Another one very interesting is this automated heavy vehicle. This is in fact this is an autonomous truck. Um, it was initially conceived to be used indoor, but currently we are we do not have access to the current developments of in the scope of this project. But at the time that we were involved, we used extensively our own library to design and assess robustness of the entire control system that provided autonomy for this vehicle. As you can see, it can be used to push heavy loads and maneuver them, and it is exactly as we expected. It is used it is commonly used in contact with hard soil and not soft soil. So the heavy dynamics library is a very nice fit for this purpose. And this vehicle was able to travel many miles using the control systems that were developed using our heavy dynamics library. And currently it is still running based on these models, which were very accurate at that time. We did not have uh, measurements in detail about the dynamics or even the geometry of the vehicle, and using the multi-body library, we could um, uh, produce a very precise multi-body model. And um, while analyzing the uncertainties of the model, we could change some geometric details and verify if our control system would be able to achieve the the performance metrics that were meant at the beginning of the project. This is a current project. It's a smaller robot, and in fact, it's not just one product. Um, eh, it's two projects in one, because this basis is like an AGV, an autonomous ground vehicle, and this structural basis can be used to put a specific load on it, a specific payload, which is used to push feed to livestock. It is a very interesting application, and there are many robots used for this purpose currently. At least five or six different manufacturers are already doing their specific robots for this purpose. But the one interesting characteristic is that this is an AGV platform, which can be used to push any kind of load indoor, or even work as a feed pusher for livestock. During the design of this platform, we had to define accurately the amount of power which would be needed to drive the wheels, and to analyze the trafficability as well by checking if the lateral slippage was too high or not, and if the control system would work even in the presence of many uncertainties like the position of the center of mass, backlashes, and many other uncertainties that we know that we are going to have once the mechanical system is finally realized. So after materialization, we know that the final version of the robot is not look quite similar to the one that was initially predicted during the engineering design phase. We know that many uncertainties are going to take place, and even in face of these uncertainties, the control system must work and meet the requirements. And in this situation, the robustness assessment is a very important thing, because the mechanical design, electronics design, and even the control design of the inner loops for current control of the motors, torque control, speed control, and so on, they should run in parallel, and at the end they shall work seamlessly in perfect harmony. But they are always considering models during the whole process of engineering design. For this reason, robust assessment was very interesting, and in fact, this is one of the most important things that we do with these models. Uh, this is how a model with heavy dynamics library looks like. As you can see here, we have many components which are basically inherited from the multi-body systems library, like those rigid links, some joints which are inside the driveline model, for example, Ackermann steering model, and so on. But the most important detail here is this component. As you can see here, we have four wheels. Some of them are powered, some are not powered, and we have a precisely defined contact model for each of these wheels that produce simulations just like those you have seen in the previous slides. So this is how it looks like. This is a very simple multi-body model with contact with with the ground. So the vehicle is completely free. There is no joint um, defining its relative movement to the inertial frame. This means that it stands basically on its wheels, and it solves the problem of static indeterminacy by considering a stiff contact between each wheel and the ground. Uh, Now let me talk about the PMSMC library. PMSM means Permanent Magnet Synchronous Motors, and C stands for control. This library, the main objective of this library is to serve as a toolkit to design and verify controls for motors and generators. We have many different models there, and they are modeled also considering multi-body library, because it would not be necessary to use the multi-body library, but as we want to integrate these models with those from, for example, Heavy Dynamics library or Aquanaut library, we are always trying to make them compatible with each other. Um, as you can see in this picture, we have some motors which were designed based on this library, and some inverters and controllers that at some point have also details verified at this library in many different aspects, like for example the details about the gate drivers, about the SVPWM uh, modulation, the character magnetic and thermal characteristics of the motors, and so on. And this is basically conceived to be used as a tool for product design, and not like the previous ones, which for um, were conceived for system design. So here, the main um, the main results are products which were designed using the elements of this library. This helps us to check how the the motors work in transient phases of the inner current loops, and check if uncertainties in the inductances or flux linkage or any other characteristic of the motors and generators would cause any type of difficulty in in thermal um, i- i- with respect to the thermal management of the machine, or even any difficulties in controlling, for example, speed, position, and um, current of these motors. This is how one of these models look like. As we can see here, we have models for space vector, PWM modulation, um, three-phase inverters, current sensors, transformations from ABC frame to DQ frame, DQ to ABC, alpha, beta, and so on. And of course, the models of the motors themselves. The model of one motor is works like um, uh, considering as the rotor being the plant to be controlled, a pure inertia with magnets in there which interact with the electromagnetic fields generated by the stator. These items are modeled separately, and they only find um, they are only able to run in a complete simulation once you put all these pieces together. So, looking into the details of one of these models here, like this motor, you are going to be able to see that the rotor, the stator, and any aspect of the windings, the thermal model, and so on, they are all designed in such a way that they only work if they are put together. And as in the real case, this motor is not gonna run if you don't have a uh, a closed loop for current, and subsequently closed loop for angular velocity as well. And our last uh, set of applications comes uh, from our newest library, the Aquanaut library. This one was designed to simulate vessels, most specifically for uh, small tugboats. In this case, I'm not allowed to show too much details about this library because this is an ongoing project, and um, there are information from other companies that may somehow uh, become available if I show some more detail. But as you can see, it's able to simulate the contact between a vessel, a pure hull with the water, and it computes buoyancy, radiation induced forces, viscous dependent forces, and so on. Um, this is how it looks like. These components here at the right side are a hull, buoyancy forces, radiation induced forces, ocean ocean currents in this block here called stream. And just like in the previous libraries, it is 100% compatible with multi-body library. It allows one to run simulations and verify everything visually, just like those animations that I presented before. And it is very interesting to see. Also, we have the models of the waves that are also provided as inputs for this model. We can see if the boat is floating just like expected according to the motion of those waves. Just like in the other libraries, everything was based on a very concise and consistent basis of of academic references. This one is mostly based on the works from Faltinsen and Thorfossen, but there are other authors as well that were used here to 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 help us to create the force models accordingly. Um, so, what are our next steps? First, I would like to remember that currently all these models they are used in a very broad sense because we use them in the phase of analysis. I mean, prior to having a materialized and implemented controller, we model everything and run many different analysis in virtual time, not in real time, and uh, check how are the most probable experiments that we should realize. It helps us to plan real experiments with the vehicles, and additionally we use these simulation models to design the controllers. After designing the controllers, we check if the controllers are sufficiently robust by means of robustness assessment. This means that after a controller um, is already designed with its topology defined, with the parameters synthesized, and so on, we keep the controller unchanged, and then we change the plant. By changing the plant, I mean we change the position of the center of mass, we change the friction coefficient of the surfaces, and many other parameters which are in fact uncertain. and we are only going to know them once we are able to run tests on the real system. But we want to to know in advance how our vehicle is going to behave prior to the field tests. Mostly because these vehicles, they are heavy, they are almost always considering people around it and so on, and many in test conditions it can be very dangerous to run these tests. So for this reason, the robustness assessment is almost mandatory during the control design. Um, Currently, what was not mentioned is that we take these very same models which were used to design and verify the the controllers. We generate real-time FMUs with them, with the exact the very same models, and export these FMUs to be used in our real-time hardware in the loop platform. Here you can see a worst case execution timing analysis. Um, this is done automatically in our tool. Once we have a specific model available, we run this worst case execution time analysis on our um, Linux preempt based tool, and it tells us in which rate it's able to run our models in such a way that we can tune our communication delays, our step size for the numerical integration, and so on. And the final controller, which is implemented in some off-the-shelf computer, can be tested against uh, this very same model, but at this time considering real-time characteristics. It is not as before running on a desktop computer with no timing constraint. In this situation, timing constraints are already present there. And what we are seeking currently is deeper integration with Modelica tools, like for example, System Modeler. This entire framework, as you could see, was used and validated in many different projects. And what we think would be very interesting would be to have these two more seamlessly integrated into uh, some specific tools in order to make it even more uh, easy and straightforward to deal with. And that's it.